Hey, what's up, people? We're going to take a break from the TVs, the CRTs, and the RGBs and take a look today at this DG02 ECM 2.3. How's that for a rhyme?
Boo!
Um, Anyways, I can already hear some people asking, what's a DG02 ECM 2.3? Any potential HVAC people out there in the audience are probably going to be like, oh, I know exactly what that is. In all honesty, I would not have known what this was either if I hadn't been the one that pulled it out of the equipment it was installed in. But if we take a look at this label right here, right above these connectors, we can see that it says a warning, high voltage, allow 5 minutes after power is disconnected before opening motor. So that's our big clue right there. And there's no shaft or anything sticking out of this, so it's obviously not a motor itself. So what this is actually a motor controller. So what did it come out of? Well, if you're interested in a short story and a bit of info, just keep listening. If you're just here for the teardown, that's all good too. I wouldn't want to listen to me either. So just skip now to whatever time like I put up here, and I'll probably see you guys there. Well, one of my brothers told me that the heater at my mom's house wasn't working, and I'm not like HVAC man or anything like that, but I figured I could try to help them out. I pretty much only have experience working with our own furnace here at home. Well, after doing some inspection and testing, I determined that the most likely problem had to be something to do with the motor controller on the blower. And I found some information online on how to test these, and it turns out they can be pretty easily tested by just applying like 24 volts AC to some of the pins on the control header, which is this 16-pin connector right here. So I made these test leads to make it easier to test, and I used the transformer on the unit itself to apply power to the pins. But I didn't have this made when I initially tested the controller, so I had to like manually jump some of this stuff on the board and like terminals with these picks and some of like alligator clips. But it was enough to rule out any issues with like the control board inside of the furnace. And this top connector here with the 5 pins, this is where you input power. So this can either be 120 or 240 volts, depending on whether or not there's a set of pins that are jumped with like a little bit of wire. And power needs to be applied before you can actually test it. So when I tested this, you could tell that the motor was trying to work. It would like very slowly like try to rev up, but it was like so impotent that you could pretty much just pinch the shaft with a couple fingers and get it to stop. And at that point, I had already ordered the replacement controller, and I just used the little test jig here to confirm that the old one was for sure bad and that the new one was going to work. And one thing you need to know about your motor is whether the blower rotates clockwise or counterclockwise. And looking at the blower from the shaft end on this unit, the motor rotates clockwise. When I looked for a replacement unit, I looked for one that had like the same model number and had clockwise as its rotation direction. And the one that I bought said CWLE on the description, and that's where I messed up. I didn't realize that the LE stood for lead end, and basically that just means that that's the direction you'd see the motor rotating if you look at it from the end where the leads and the wires come out. Well, I installed the controller on the motor, and I applied power to the test leads, and the motor rotated backwards or counterclockwise. If I had bought one that was sold as counterclockwise LE, then I would have been fine. So I had ordered the correct direction controller, right? Well, I didn't want to leave my mom with no heater for like several more days since the weather had been like pretty cold. And as it turns out, the motor itself is basically just like a large brushless DC motor. So switching a couple of the leads around and repinning the connector going from the motor coils to the controller should get it to rotate in the proper direction. And I didn't want to like cut any wires, so I asked my brother who was helping me up in the attic if he had something that could help me remove the pins from the housing, as I didn't have like the right tool with me, which would have been like this one right here. I ended up trying to make something out of a piece of a beer can, but that didn't work. And we also tried some sewing needles, and that also didn't work. So I finally just had to jump back in my car and run home and pick up the right tool, which made it like ridiculously easy to do. And I believe this is a Fillmore 61-390. It's meant for 0.093 inch female pins. So the way that this works is that you'd have like the female pin in the housing, and this thing just kind of like slips over it like that and compresses the two little tabs that would, if this would focus, that would like normally hold it against the housing. So it compresses that like that. You just push on the plunger and it pops the pin right out of the housing. So I wasted more time trying to figure out a way to pull the pins out than it took me to just go home and come back with the right tool. So I did write the original position of each of the colors onto the housing before I repinned it, and for future reference, like just in case. I wasn't sure if I was going to be able to get the wiring right on the first try. But it appears that the controller tries to like gently spin up the motor. So if it didn't work properly, I could try like a different combination. Plus the motor's like sensorless, so I figured worst case scenario, the motor would just kind of like bounce around like back and forth if the wiring was wrong, and I could just, rearrange it. So after doing that, replacing the ECM back on the motor, the blower finally rotated in the correct direction, and so I reassembled everything, and it's been working great ever since. My mom even sent me a message the other day saying that it's been working great, so I'm pretty happy about that. Unfortunately, from what I found online, it appears that these controllers are pretty problematic and they are known to frequently go bad. When I tried to find a replacement online, all I could pretty much find were pulled used units on eBay, and I didn't know why. But I guess it turns out that they're no longer made, and there's like an updated 3.0 version replacement of these. I didn't find out about that until after I had already received the replacement. But it appears that the correct replacement, the updated replacement for these units is part number HK46EA123. And I also kept seeing things about these needing to be programmed, but I haven't looked into it or how it's what's actually done to program them. Or I think the thing that changes is something about like the airflows. Another option for these is to basically just replace the entire motor. That was going to be about like $800. And the unit that I found to replace this one was ended up costing like a total of about $140 shipped. And it seems to be working totally fine. And my mom is happy, so I'm happy. So anyways, let's take a look at this one. We'll tear it down to see if we can figure out what failed. And now, as like a lot of you will already know, being that electronics fool, I normally don't like to just like replace entire modules without trying to fix the original one first. But there was two main reasons why I decided against it in this case. One, I didn't know how long it would take me to figure it out. I wanted to try to get the heater going like as soon as possible. And two, if we remove this board from inside, it's got a little plastic standoff right here that has to have these pins pinched together. So yeah, if we look inside, we can see that everything is potted in silicone. So trying to dig it out could potentially be destructive if I wasn't like careful enough. And I didn't want to risk wasting too much time on it. But thankfully, it's just silicone and not epoxy. So it shouldn't be impossible to dig out. It's just going to be time consuming. So, I mean, just looking at it like that, we don't really see like anything bad. We can see right here on the side, it's got this sort of like aluminum heat sink up against the casing. And it's got what's going to be, pretty sure that these are going to be like 6 MOSFETs right there. So that's for each phase of the motor coils. And looks like we've got some maybe like filtering or something right there. Or these could possibly also be like gate drive transformers. So this board up here, this is the power input board and like filtering. So power comes into here and it goes through like this big like common mode choke right there. It got some capacitors. And I've seen some videos and stuff of people talking about how to fix these. But the only thing they ever really do, it seems, is like replace this thermistor right here. What I've seen in some of the images is that like this thing will like either fry or like blow out or something. So it doesn't allow power to go like through the this rectifier board anymore. And unfortunately for this one, it does not appear that this is the problem. So it's going to be something with the actual controller itself. See, we've got 2 big capacitors over here. So I'm actually going to start by removing these 2 leads right here off the board just to make it easier to be able to like, move this around so this isn't like swinging all over the place. And the reason why it says right here on this label to allow 5 minutes after power is disconnected is because these capacitors right here are obviously going to be storing like a pretty decent charge. And it does look like they do have bleeder resistors right there. So they are going to discharge. It's just going to take a bit just because of their size and their 1000 microfarad at 200 volts. All right, so I'll start with that. I'll remove these 2 wires off of this board, and then we'll see if we can dig out this board from the rest of the casing. The soldering iron is hot, and this board here is conformal coated, so it's going to have to kind of, melt through the plastic there before it can, or the coating before it can get to the pin. All right, there it goes. It's starting to melt, and it's wiggling, and I'm trying to pull on it as it melts. And this is going to be one of those annoying pins that has like a couple tabs that extend outwards. There we go. It came out, and yep, those little tabs right there. They kind of hold the pin in place, and it makes them kind of hard to remove. See, it looks like it might be on this side right here. So I'm going to try to push in on that while I heat the pad. And if this thing would stop slipping. All right, there we go. I got it. Okay, maybe that's not it. So I'm just going to try to like push in on different areas and try to get to that pin. There we go. I got it. So it's a matter of finding where that pin is and pushing in on it so that it bends it inward so that it can pop through the hole and come out just like that. So that's that board. We can see right there we've got a diode bridge or a bridge rectifier. So coming out of this, basically it's just going to be like a DC power going into the main controller board. And so now I think we should remove these bolts right here holding that heatsink on. That's pretty much going to be the only fasteners it looks like. I mean, I don't even know if it's going to be possible to repair this or not. And like I said, I don't know if this is also going to be kind of destructive or not, because trying to dig out this much silicone out is going to kind of a pain in the butt, but let's see. Okay, so that's all three of those out. Maybe if I try to like cut around the perimeter, that might help me out a little bit. You know, take this blade here and see if that gets us anywhere. I'm trying not to go too deep because I don't know where there are. I mean, there's probably not going to be any components like really close to the case. I mean, with the exception of like the MOSFETs, but just in case. Then again, we see that these leads right there, they go in like pretty close to the edge of the board. I wonder if maybe I can get a screwdriver down in there and kind of like pry it up. Let's see. Nah, putting a little too much force on that. So I'll just keep trying to dig out the sides. Well, I guess these little tubes right here, they're just to guide the screws when this is getting installed onto the motor. It guides the really long screws that hold the this casing onto the back of the motor so that they don't like, you know, go around like sideways or anything like that. So these should be able to come off relatively easily. Maybe let's dig around it a little bit first. Okay, there we go. I ended up having to kind of smash the end there a little bit, but that's out. And let's get this other one out. Okay, so unfortunately, and I knew it was going to happen like really soon, I just didn't know exactly when, but the batteries on my microphone died, and so I have a little bit of footage that I recorded that had no voice on it, but luckily it was only just a tiny little bit because I caught it in time. But what I was doing was I was using this little plastic spudger here to try to dig some of the silicone out, and I'm trying to get like big chunks of it out, like as big as I possibly can. And I'm using this plastic one here to hopefully prevent like damaging any of the components that might be like on the board. We can see that we're already starting to see some of the board right there. And there are surface mount components on this. So hopefully using this plastic spudger will keep me from damaging it. But basically what I'm doing is I'm just kind of like gently trying to push it in and pull out as big of chunks as I can. So I'm just going to continue doing this until we get to a point where maybe I can try to pull this board back out. And it could be that this board doesn't actually cover the entire bottom. It appears that like right here, looks like it just has an opening, and the spudger here just goes all the way down to the bottom of the case. So if I can remove enough of this silicone from what's just the top of the board, then maybe we can like peel it off of whatever's holding it down there on the bottom, and maybe it'll come out that way. But yeah, this is going to be very time consuming, so I'm just going to do all the digging off camera, and we'll be right back. I spoke too soon. Check out this big chunk that I got here. It's like peeling off the board pretty good. There's something there that's stopping me from being able to pull it, but yeah, this is going to be a really nice big chunk. Oh wow, there's like a 40 pin device down here. I was expecting maybe just like surface mount stuff. Oh, that's not a 40 pin device. It's more like a 28 or so, or 24. Okay, so I think I've dug around the perimeter of the board down here as much as I think I can safely do. And what I think I can try to do now is pry it up from the end here, maybe, like where this connector is, and try to get the board to separate from the bottom layer of silicone. And just trying to be very careful there. It's lifting up and it sounds like the silicone is detaching, but I'm trying to go slowly. Seems to have detached a bit there. See if maybe I can use a pick to help me pull up on these little cutouts right here. Hopefully I don't impale my hand in the process. Not gonna lie, this thing is killing my hands just trying to dig out all that silicone. Don't seem to be getting anywhere here. Okay, it appears that there's a layer of plastic underneath the board right here and the casing. So that's probably for insulation so that like pins protruding from the board like don't touch the metal. So maybe if I can try to like push it out from underneath here, I can get the whole thing to pop out. All right, I think I'm finally getting somewhere. So this is actually moving quite a bit now. And I'm trying to like stick this in through the top here and pry up on that little cutout. And trying to pry it from two places at once. And it's slowly coming up, but it's coming. Maybe if I just take turns prying like side to side. Oh, there it comes, there it comes, there it comes. There it goes. Got one side mostly out. Looks like it's still stuck over here. Keep pushing it from the very bottom over here. There we go. It's loose, but still has yet to pop out of the out of the case. Ah, there we are. Not gonna say that was a pain, but it was quite the pain. All right, so now we just have to dig this, the rest of it out. So yeah, there's that plastic covering. Maybe I can peel off the bottom like this. Nah, there's gonna be a lot that's gonna stay stuck on there. But it looks like a lot of it is gonna come off though. Ah, I should have cleaned the heatsink paste off of that. I got a little too excited. Ah, there we go. And we still can't see a whole lot of stuff, but there is a lot of surface mount components and stuff in here. All right, well, I guess I'm going to be sitting here for a while just trying to dig all this stuff up. And it appears these are not MOSFETs. These are probably going to be IGBTs, and we can tell because we see there's a G there, a collector and emitter, so that's going to be gate, collector, emitter. So probably just some high voltage IGBTs. At this point, I've got maybe about like 90% of this thing dug out, as you can see there. And I thought I'd kind of show like the little process I'm doing here. So I'm just using this a little plastic spudger here. And for like wide areas and where there's like a lot of material, what I'll do is I'll try to like insert the flat end in there and just kind of gently but forcefully try to get some of the silicone to like come up. There are a lot of like surface mount components, as you can see. But the good thing is that this plastic one, it doesn't immediately like damage any components if you're careful enough. If you feel it, you know, I stop kind of like pushing a little too hard. And so I get like rather large chunks out of some of the areas like I just did right there. So right here, it seems like it's relatively flat. There are no surface mount components. So I can just go ahead and scrape up some of this stuff right there, like flat up against the board. And it'll come up like that. But then for areas where there's a lot of surface mount stuff, I'm using the sharp end, and I just kind of go through and scrape in between like all these like resistors and capacitors and stuff like that, and just try to like fit it in there as much as I can and move it around like side to side. And so this gets a lot of it out of there, and then I can kind of just like scrape the stuff off like the top of the components there and expose to see what they are. So yeah, this is going. It's just a bit of a slow process. Been sitting here for a while now working on this, but as you can see, it's coming along pretty good. I keep bending like all these components here, but yeah, once it's all dug out, we'll see what kind of stuff we can see and see if we can maybe identify what went wrong. And as you can see, I've got the majority of this pretty much almost completely excavated, with the exception of stuff that's like over here where I can't quite get the this pick to or spudger to clear away some of this stuff here. And I don't feel like rubbing my fingers away by trying to do that. So I thought if I have like a stiff bristle brush, maybe I can use that to loosen up some of this stuff. But I didn't want to use like wire or anything. So if I had like a really stiff plastic bristle brush, maybe that would work. And I do have these anti-static bristle brushes. That's this one's, it's pretty stiff. It's not like crazy stiff, but I think it might work. So let's see if this will do it. And yeah, that seems to be working pretty well. Got stuff trying to fly off all over the place, so I'm going to see if maybe I can cover this up a little bit. Keep it contained. And go in like various directions to try to get like underneath and to the sides of some of these components. Yep, that's going to work. So I'll try to finish it off with this. One step closer. Oh man, would you look at this mess? So I put these two pieces of foam board here just to catch any like small little pieces of debris that were gonna inevitably fly off as I scrape the board. And if you look at this one right here, you can see that there's like a bunch of tiny little like silicone little particles that kind of like just sprinkled all over that piece of foam. So I'll clean this up and then we'll take a look at the board. While I was cleaning the board off with this brush, I was expecting this brush to get like absolutely wrecked with all of the like pins and, you know, resistors and all that stuff that it had to like rub up against. But if we look at the bristles up close, they barely look like they've been touched. The only place where we can see some obvious signs of damage is like on the side of the brush there, where like I believe I would have like scraped it against like some pins or whatever from trying to get like on the sides of like these resistors and capacitors and all that stuff. But as far as the bristles go, I mean, they look like they're pretty much like brand new out of the package. So these are like some cheap brushes, but they totally exceeded my expectations when it came to cleaning the board off. Okay, so here we are. It actually looks pretty good, minus the fact that there's still like stuff left on these like transformers right there. There's stuff between the pins of all the ICs and underneath, but everything else cleaned up pretty well. And so what we can see, well, let's look at the bottom real quick. So even the bottom cleaned up pretty good. I did do a tiny little bit of damage like in here in the middle where I was trying to pry up with the screwdriver, but I didn't break any of the resistors or anything. So I was a little worried that I had actually broken some of that stuff off, but I didn't. And so, yeah, a lot of it cleaned up pretty well. So we can see what everything is and how it's hooked up, so we can see if we can identify what the problem is. So looking up here at the top, we see that we've got a total of 1, 2, 3, 4, 5, 6, 7 dip packages there. And what all of these are is this is an LM339. So that's going to be like a quad comparator. And then this IC right here, I'm not sure what exactly it is. It's got GE ECM-2 AHDC like written right there, as well as it says up there 8794 723K, but I couldn't find any information on that. And ironically enough, I said we weren't going to talk about TVs or anything like that, but that ceramic resonator right here, that's a 3.58 megahertz ceramic resonator. Now, why do I say or mention TVs and stuff like that? Well, that's because that's the NTSC like color burst frequency. It's a 3.7 or it's a 3.579545. So that's like a color burst frequency crystal right there. So I just thought that was funny. And this chip right here, that one says 20 TWP5. I also could not find like any data sheets or anything for that. So I'm guessing that this one is probably the microcontroller. It also says Rev 3 right there. And the only reason I say that I think it's a microcontroller, it's because there is a 93C 46B EEPROM right here. And that appears to be connected directly to this IC. And I would have thought that maybe this was the microcontroller, but I actually think that this is the motor driver, and it's syncing everything using like this ceramic resonator over here. So maybe there's an output from here to drive the microcontroller for its like clock input. I'm not entirely sure. And I'm not really interested in taking these off the board or anything like that, especially since I can't like find a data sheet or anything for those. So yeah, EEPROM, possibly microcontroller, a motor driver, I'm guessing. And then we've got these other 3 packages right here. And all 3 of these, they're all optocouplers. So a bunch of the stuff that's interfaced on this pin header right here, that's all going through the optocouplers. So basically it's isolating signals from in here to the signals coming in. And that also kind of makes it a little bit safer where if like something shorts or happens like up here, it won't really damage anything inside because there's no like voltages like going up here to like do pull-ups or anything like that. And so these 2 right here, these are quad optocouplers each. So there's a total of like 8 optocouplers right here. And then this one here is like a single optocoupler. And I believe that this one here is probably for output. And it's probably for like a pulse output for like the motor rotation. Because I believe that there was one of the pins here that's basically used as like a TAC output. So I think that's what that one there is doing. So that's also basically isolated from the rest of the system. As far as all the IGBTs or insulated gate bipolar transistors, these are all labeled N60 UFD. And I did find a data sheet for these. It's basically they're like ultra fast IGBTs. And these little 3 transformers that I said were probably gate drive transformers. They appear to be, but the way they've got this organized here is these 3 IGBTs in this area, 1, 2, and 3. These are all the high side IGBTs, and these here are the low side IGBTs. So these are connected directly to the negative input or the negative voltage input, whereas these 3 top ones are connected to the positive input. So these transformers are for driving the gates of these 3 up here, and these 3 for the bottom side. These are all controlled by, it appears that they're probably going to like over here to this chip, from what I can tell from just kind of like looking at some of the traces. And since the motors that these are used on are sensorless, I believe that they're using basically a back EMF to detect the position of the rotor. So it looks like all of these resistors right here, they're all like in series per like connection right here. So they all appear to be going to this LM339, the quad comparator. And I think that's how they're getting their signal to let the controller here know like where the rotor is like currently positioned. So it knows like when to set the next set of coils, like active or switch the polarity on one of the coils or, whatever. So I believe that's how that control there is working. There is a resistor right here, like a really low resistance resistor. And I'm pretty sure that this is probably for current sensing. This is connected in between the negative coming in, the high voltage negative, and it's going to the low side drivers over here. So it appears that there's like some small traces coming off of that. So if we look at the other side right there, we can see how this trace right there kind of goes off into here. And then it went off like right here. So that's going to the emitter side of all of these IGBTs. This other section right here, this appears to be the low voltage section. So it's converting the 300 some volts that are going to be coming into these lines. And one of them goes to that diode right there. And I think that's probably going to be like a Zener diode. So it's making the voltage a little lower on that side. But these 2 devices right here, this one's a LM78L05. So that's like a very low current 5 volt regulator. So that's going to be off, going off over here and like feeding like this IC, that IC most likely. I don't know if this one's going to be fed off the same thing. I'm not sure if this one, I haven't quite traced everything yet, but I don't know if this one here like also requires like a 5 volt input or something like that. There is another transistor over here. I think that this one might be being used as a linear regulator because this diode right here is probably going to be another Zener. I haven't done a whole lot of tracing on that side either, but I'm guessing that that's probably what that is. So it's probably using like 5 volts and maybe like 12 or 15 or something like that. That might be being used for like driving the IGBTs or something. Maybe this is what's regulating that voltage. This cylindrical device, this is an inductor. And there is another device right here, another surface mount MOSFET. And this is an IRFR 120. So it's basically another N-channel MOSFET. Not entirely sure what that one's used for either, but it looks like it goes directly to the positive input here. And maybe it's being used as like to cut off power if there's some issue over here, or maybe it delays like turn on or something to the rest of the circuitry. Not entirely sure about that one. But as far as like anything obvious here goes, there is nothing that's showing like any obvious signs of damage. I actually checked these IGBTs all for shorts, and none of them appear to be shorted or anything like that. I did a diode check between the emitter and the collector, and those are all showing up fine on all 6 of these. And unfortunately, with these, we can't really test like do a diode check between the gate and the collector and emitter because it's like an insulated gate, so that doesn't work. But like I said, nothing obvious on those. Nothing looks burnt like anywhere on this board. And on the bottom side, like, yeah, nothing appears burnt or damaged or anything like that. And so I mentioned that it appears that it does try to work. And actually, I am going to put in some clips of what I recorded when I was trying to test this one out when it was still attached to the blower. And so I'm wondering if maybe there's a problem with the low voltage side of the circuit over here. Maybe it's what could be happening is that the motor tries to like start spinning up, and when that happens, the voltage over here maybe like dips a little bit, kind of like browns out, and then the microcontroller maybe has like some like brownout protection where it resets the IC if the voltage drops too much. And so maybe that could explain why it appears to try, but it's like really weak because it's trying, but it can't, like fully spin up and it keeps resetting. So I'm wondering if maybe one of these capacitors or more than one of these is possibly bad. And unfortunately, I don't have like a motor on hand that I could, like probe around and try this with. But the fact that it's like potted and it's like very difficult to remove and get to just makes like the effort of trying to repair one of these like a pretty like too much of a hassle, I think. So there is one little piece of wire right there from this transformer that's kind of loose, but that was my fault when I was trying to pick in there to remove some of that silicone. I accidentally like popped it off, so I broke it free from the pin that's supposed to go to the board right there. So that was not damaged, and I actually did check continuity between all of these coils. So they're all arranged kind of like this one to this one to this one, and then like on here it would be like that one to that one, that one to that one. So these all appear to be good except for the one that I popped off. And the fact that it does try to work also kind of indicates that these optocouplers are probably fine. All this other stuff like that's around here, there's a lot of diodes, and there's one like transistor, as we can see like right there. But for the most part, a bunch of these are diodes. So they're pretty much basically probably just taking the inputs here, because as I mentioned, you can feed in like AC voltage to the inputs and make the motor turn on, all that stuff. So they're probably just for being used as like a bridge rectifiers, basically, and rectifying the voltages coming in. And on the opposite side, we can see we've got like a ton of resistors. So these are probably going to be like for current limiting and stuff. And there's just so many of these, like 242s, 202s. This is kind of blurry. Yeah, right there we see a bunch of 242s. So these would be 2.4K resistors. These would be like 2K resistors. 102, those would be like 1Ks, 1.2Ks, 470. So yeah, a bunch of resistors all up in this area. And we can see right there, these are the pins that go to the optocouplers. These are the pins to the 16-pin connector for the control. And while I've got the microscope here, we can see how the input or the connector here for the motor, we can see how the three traces or 3 connectors here go to these 3 traces of resistors, and how these are all like in series. So then this right here looks like maybe it might be kind of like a voltage divider or something. And then we've got some smoothing here by way of these 3 ceramic capacitors. So then this stuff all looks like it goes over here to the LM339. So as I said, I believe that this is probably being used as part of the circuitry for the back EMF. You can see how some of this stuff goes out to this chip right here. So yeah, as you can see, just from doing a close-up here, nothing appears to be damaged or burnt. I think the easiest thing we can do is maybe like check these capacitors and see if like any of them are like below their rated values or something, because there really isn't a whole lot of stuff that I can check on here, especially with these being like all possibly like custom. So yeah, I guess we can at least check that. We'll check these capacitors here and see if that gives us any answers. Okay, so I pulled all the capacitors off the board and I quickly went through and tested them. And I sort of did like a little diagram here of where I pulled them from on the board just so I could better keep track of them without having to like pull off one at a time and check it. And so what I did is I just marked them here with some paint marker, and that way I could easily tell which one was which and write it down over here. So starting from number 1, which is the one that's colored red, these are all 22 microfarad 50 volt capacitors, and this one here is a 4.7 microfarad 50 volt capacitor. So it was the only one that was different. So the first one, the one that would have been like in this position right here, that one tested at 16.5 microfarad and had an ESR of 11.4, which just looking at some general charts, seems like it's a bit high. And for us to have like a minus 20% value of the 22, we'd have to be looking at something about 17.6 microfarad or equal to or greater than that, for it to be like within spec. And this is definitely below spec, so this kind of suspect here. Capacitor number 2, which would have been the blue one, which would have been right here in that position. That one also tested low, and this was actually lower than that one by about 1. So yeah, that one measured at 15.4, and it had a ESR of 14.7 ohms as well, so that's also kind of on the high side. And so those two are, it looks like at least for sure that one right there, the one that measured the lowest, is definitely coming straight through this diode here. And as I said, I think this might be a Zener, but I can't read the entire number because it's kind of covered. But so I think the high voltage comes through there, and then it's basically limited a little bit by that one, and then this capacitor here helps to smooth it. So maybe that capacitor there has degraded to the point where it's no longer working properly. This capacitor, I'm not exactly sure how it's connected here in the circuit, but it is also tied to the negative point right here. So that could have something to do with some of the regulation on the input as well. So yeah, both of those are right here on the technically no good side. So number 3, the orange one, that one measured 4.8 per micrometer and ESR 5.6, which is kind of low. So technically this one would be good from what I measured. And then the other two, they were 17.8 and 19 microfarad, and those were the ones over here that are on the 5 volt side. So one of them is for like the input of the 5 volt regulator, and the other one's this one here would be for the input of the 5 volt regulator, and this one here would be for the output. So those two are technically okay since they're both above 17.6. I mean, this one here is kind of like marginal, but technically these are fine, although they are more on like the low side. So if anything, I would suspect at least like these two here being problematic. This one here doesn't look like it would be a problem. And so if I were to try to test this to see if those make a difference for sure, I'd for sure like replace those. Although, as I said, this thing's really not designed to be like serviceable in any shape or form. So don't take this as like a repair guide or anything like that. This is just me trying to investigate this a bit and see if it's possible to figure out what exactly went wrong with it or what goes wrong with these units. As I mentioned, some of them, they have that thermistor that blows. This one didn't have that, so it's going to be something on this board for sure. And one other thing I can possibly think of is maybe this quad comparator could possibly be bad. And I say that just due to the fact that since it tries to rotate the motor, it's possible that it's not getting the feedback, or this isn't actually doing its job and providing feedback to the motor controller IC. And so this one here has no idea what's going on because this one here is not propagating the information over to the inputs of this IC. And so it tries to spin it up a little bit. It gets no feedback. And then, it tries some more. And it's just like gently trying until it gets something, but maybe it just never does. So this is, it's probably one of the only other ICs that I could suspect, I mean, other than these two, but as I said, these are, can't find any data sheets, and they're not something that you can just, like buy or anything like that. So I think that I could probably rig up like a quick little test for this one and see if we can find out if this one's fully working or not. It would just be a matter of applying like positive and like a ground or something to two of the pins, and then rigging up some resistors and stuff and checking what happens at the output when those are like adjusted between like a certain like voltage threshold that's set on the opposite pin or something like that. So I'll remove it just for the sake of the science here, and we'll see if this one could potentially be an issue as well. Well, I didn't think about taking any footage of this, but I was able to get it off without like any damage. So first I applied like some flux to the pins there, and I used the solder vacuum to pull as much solder as I could out of them. But because the chip was still attached to the board with like silicone underneath, it wasn't just going to easily pop off. So what I did is I took my little hot air station and I heated it up, trying to get the, whatever leftover solder was there like to melt. And then I just took a couple of pliers here and I just gently was rocking it like as I would heat up, just kind of back and forth a little bit. And so it started loosening up, and then I was able to just like completely pull it straight off the board there. So it sustained like no damage whatsoever. And I think it should be good to for me to be able to test it. So yeah, let's see what I can do here. Okay, so here I've got the test setup, and coming into the board, we're going to have 9 volts. And right here, I have an LED that's going to indicate whether or not the comparators are working. Now, this chip right here that I have on the board right now, this is not the one that we're going to be testing. This is just a known good one so that I could verify that the circuit is going to work properly. And so this LED, it's connected, the positive pin is connected directly to the positive 9 volts coming in. The negative side, or the cathode, goes through a 680 ohm resistor over to this wire right here. So when this wire gets grounded out, the LED comes on. And over here in this section, we have 2 voltage dividers. One of them is a fixed voltage divider with 2 10K resistors. And then I have a little capacitor there in parallel with the resistor that's connected to the ground, just to stabilize the voltage on that this section a little bit. So the orange lead here, this is going to connect to the positive input of each comparator. And this is providing about 4.5 volts because it's dividing the total voltage in half. So that one's going to be fixed. And this one here with this blue lead, it's another, well, there's a 10K resistor down here going to ground, and there's also another little capacitor there just for a little bit of stability. And then I've got a 5K resistor going up to the positive, but this is connected in series with a 10K potentiometer. So what this allows me to do is to swing the voltage on this lead between about 3.5 volts and 6 volts. So what we're going to see is how the comparator will toggle the output depending on if the negative input is higher or lower than the fixed input, which is going to be the positive. So it's going to be checking if the negative input is higher or lower than the positive one. And if we took a look at a data sheet for the LM339, we can see in here that we've got a total of 4 comparators. So for this known good chip, we're only going to test one just to show how the circuit is going to work. So the positive inputs of each of these are the ones that are going to go to the fixed 4.5 volts. And the negative input is where we're going to adjust the voltage. And if we take a look at how each comparator works internally, we can see that on the output pin, that just goes to the collector of a transistor. So this output cannot go high or anything like that, and the voltage is really not adjustable. The only thing this can do is pull down to ground. So when the voltage at the negative input exceeds the voltage at the positive input, this transistor will turn on, and it's going to pull this output to ground. So since I've connected the LED to the output, once the voltage at the input goes above 4.5 volts, it's going to pull this down to ground, which is going to allow the LED to turn on. And here in KiCad, I just drew up a quick little schematic just to show how it's all connected on the breadboard. So as we can see, we've got the LED here. The positive is going directly to 9 volts. The negative side, or the cathode, is going to a resistor to the output of each comparator. The positive input, that's connected to the fixed 4.5 volt input with the capacitor in parallel so that it just keeps the voltage a little bit stable there. And then the negative input, that's the one we're going to adjust. We see that we've got the fixed 10K resistor down here going pulling down to ground. So we're going to be adjusting the positive side. And the reason I've got this 5K resistor here in parallel or in series with the potentiometer is so it allows a little bit more swing room, because if this was a 10K resistor, or because if this was just left at 10K, we'd basically have the same thing here, says a 4.5 and 4.5 when it's at the lowest or at the highest resistance it can be. So by putting this 5K in series with it, then I have some room there to adjust higher or lower than 4.5 volts. Okay, so let's do a little demo here real quick with the known good one. So I'm going to hook the LED up. Well, first of all, I'm going to hook up the positive here to the 4.5 to the positive input. And then we're going to hook up the low side to the negative input. Make sure that this is all the way down. Oh, and before I forget, I wanted to get the scope there on the corner so we can see that if I also have I forgot to mention that I have a couple probes here hooked up to the scope. So we can see that the blue is the blue lead here, and the yellow trace is the orange one. So as I turn this potentiometer up, you can see how the blue line starts rising. So we can swing it above 4.5 volts, which is what that yellow line is sitting at about there on the scope. So I have it set to 2 volts per division. So right there we have about 3.5 volts at the lowest point. So this LED will not turn on when I hook this up to the output. And so you can see that it's not on. So as we raise the voltage on the blue line or the blue trace, we can see that once it gets to about a little bit above 4.5 volts, then the LED turns on. So this just shows that this comparator should be working properly. So now I'm going to replace this one with the one that we want to test. And we're going to check all 4 why can't I say comparators? We're going to check all 4 comparators on the device that we pulled off the board and see if all 4 comparators inside are working properly. So I'm just going to disconnect everything here real quick. And I'm going to pop this one in. And we'll check one at a time. All right, so I've got it set up to check the first comparator. Let's see what happens. So I'm going to raise the voltage here. And it works. So that one appears to be working properly. All right, now comparator number 2. Here we go. That appears to be working properly. All right, number 3. That seems to be working properly. And number 4. So that appears to be working properly. So it seems like there's no issues with this chip. So this appears to be totally fine. So I was going through the board to see if maybe I could test these little transistors. There's both diodes and transistors in a lot of these spots right here. And a lot of these transistors are labeled 2T, and they appear to be NPN transistors. We can see that there's a few spots here where there's some that are not populated. Well, I got to this part here, and I realized that these pads there looks like they had a device there before, but there's nothing there now, and I don't think that I would have knocked them off, at least not with that little plastic spudger. As I mentioned, I was, just kind of scraping, and then if I felt any resistance, I would kind of lighten up a little bit. But there appears to have been some components there. And if we look at it up close with the microphone, we can see where it looks like little pins were like soldered to the board. If we look at some of the ones that are not populated, they do not look like that at all. But I didn't notice anything when I was removing all the silicone material. So I'm wondering if these are in the silicone somewhere in all the stuff that I scraped off. And so I put everything inside of this little tub. As you can see, there's quite a lot of this stuff in there. So I don't know if we're going to find those like stuck to the silicone in like one of these chunks here or something. So maybe I'll go through and look through all this stuff and see if I can find those devices. Well, that ended up being way easier than I thought it would be. It was like the second chunk I pulled out. And so it took me like just a minute to find it. But there they are right there. There's 1, there's 2, and this one here looks kind of weird. If we look at it more up close right there, we can see that this one here looks to be pretty intact. And yeah, I don't think my poking here would have, because it looks like I tore this piece off pretty complete there. Like it was a big chunk that just came off. So I didn't like scrape off these transistors or anything, or diodes, not sure what they are. But that one there looks like it's completely intact. This one here looks kind of weird. So let's dig these out and see what's going on with that. That one there looks like it might actually have a like a leg burnt off or something. So maybe this one's damaged. Oh, maybe I did pry these off. The legs are all bent. So I may have pried a little too hard in that spot. So, okay, so maybe it was my fault. And let's see what's going on with this one. Ah, there's the exam. Oh, okay, so yeah, it was technically my fault. It doesn't look like it was anything that happened while these were on the board and functioning. Yeah, so I didn't clean these up all that well, but enough to see that they're not burnt or anything. So the damage that they took was not from something that would have happened to it while it was in operation. I think what must have happened was when I was trying to remove that piece of silicone from in there, I must have like stuck this in there, and maybe I like pried to the side like that a little too hard, and I totally did not feel it that those popped off. Yeah, so after going through this a bit, I can't find anything that, like I said, that's showing like obvious signs of damage. The only thing that's a little bit kind of sus are these two capacitors right there. I mean, they're kind of low, but they're not like crazy low. So I don't know if that would affect it that much. But yeah, I think we're just gonna leave it at that. As I said, this wasn't really like meant to be a repair or anything like that. I just wanted to check and see if we could figure out what actually went wrong, and it's really kind of inconclusive. But yeah, if you were ever wondering what was inside of one of these things, well, that's it right there. Got all the drivers, all the controller stuff right there, some gate drive transformers, all kinds of stuff, bunch of surface mount passives and all that, and a ton of silicone. Oh, one other thing that I kind of thought was kind of interesting. The outputs here for the positive and the negative 300 some volts that it puts out, I was trying to figure out where exactly they went. And so this one here, that's the negative. So we can see that it goes to this large trace here. That goes to the negative of that big capacitor there. The positive solders right there. And if we zoom in on it, we can see that the only place it can go is through this tiny little trace right here. And that goes to the positive side of this other large capacitor there. So it appears that this little tiny trace right there is maybe being used as like a fusible link, because as we can see, there are no other like large links or anything like that would go there. So yeah, it's almost like they put a little tiny fuse on the board itself. These two here are cutouts, and we can see that there's like silicone stuff right there. So yeah, I thought that was kind of interesting. Okay, so unfortunately, inconclusive results. We couldn't quite pinpoint what exactly could have gone wrong with this thing, but at least we got to see what was inside, buried underneath all of the silicone. So I guess I'll take that as a kind of a win. So stuck around to the end. Thank you all for watching. I'll see what sorts of fun things we can look at next time. And if you made it to the end, thank you once again. I will see you guys around the bench.